This video is going to show you how to do calculations for preparing a buffer. And I'm going to do two example problems. The first one's easier than the second one. And I thought I would just mention that this is the fourth time I've done this, so it better work this time. All right. We're looking for the concentration of sodium benzoate. We don't know what that is. And we have a 0.2 molar solution of benzoic acid. So we have a buffer. And I know it's a buffer because I have a weak acid, benzoic acid, and then I have its conjugate base, or its salt, which is sodium benzoate. Now when I write the reaction, so I'm going to write the acid first. I'm writing benzoic acid plus water will give us, acid's a proton donor, so that hydrogen is going to water. We will get hydronium, and we are going to get the conjugate base, which is benzoate. Now, how I knew ahead of time that this was its salt was because the ATE tells me that this is an anion. Sodium's my cation. So I know that this is a salt because I've got two ions. It's an ionic compound. I'm going to make an ice chart and get rid of water because it's a pure liquid and we don't include it in the expression. Okay, now I'm going to substitute what I know. I know that the benzoic acid is 0.2 molar. And I know that I'm looking for, I want to find this. I want to find the concentration of sodium benzoate. So that's my X, because I don't know what it is. Before these two would interact at all, my hydronium ion would be 0. So that's what I have initially. Now I've also got a Ka, so I could write my expression, and that would be concentration of hydronium ion times concentration of benzoate ion divided by concentration of benzoic acid. Now I can substitute my Kan, which is 6.3 times 10 to the negative fifth, and then I've got to know what these values are. Well, we already said that benzoate is what I'm looking for, so I need equilibrium concentrations of these three. So how am I going to find that? The one other bit of information I'm given is a pH of 4. So from a pH of 4, I can get the hydronium or hydrogen ion concentration. If I do 10 to the negative pH, I will get 1 times 10 to the negative fourth. So that's going in on the equilibrium line. It's going right here for my hydronium ion concentration. Okay, I cannot assume that these two are equal at equilibrium because I don't know that these two values are the same. So, but I do know that if hydronium ion concentration was 0 and it went to 1 times 10 to the negative fourth, then it has to be going up by that amount. Because benzoate is also a product, it is going to go up by 1 times 10 to the negative fourth. And the other side of the fence, the benzoic acid is going to go down by 1 times 10 to the fourth. Negative fourth, I'm sorry. So here, reactant side, I get 0.2 minus 1 times 10 to the negative fourth. I have hydronium ion concentration. I got that from pH. And then for benzoate, I have X plus 1 times 10 to the negative fourth. So I have all of the equilibrium values that I can substitute into the expression. So I will have 1 times 10 to the negative fourth for hydronium, X plus 1 times 10 to the negative fourth for benzoate, and then I'll have 0.2 minus 1 times 10 to the negative fourth for benzoic acid. Okay, so now I need to solve. So I'm going to do 0.2 minus 1 times 10 to the negative fourth. That will give me 0.1999. I'm going to take that times 6.3 times 10 to the negative fifth, and I get 1.259 times 10 to the negative fifth. That is equal to 1 times 10 to the negative fourth x, because I'm distributing here, plus 1 times 10 to the negative eighth. Okay, I am going to combine like terms, so 1.259 times 10 to the negative fifth minus 1.0 times 10 to the negative eighth. I'm going to go to 3 sig figs here, so 1.26 times 10 to the negative fifth is equal to 1.0 times 10 to the negative fourth x. If I divide both sides by 1 times 10 to the negative fourth, I will get x. It's kind of a boring color. I will change that next time. 2 sig figs, 0.13 molar. Now that tells me my initial concentration of benzoate ion. I want to show you one other thing that we could have done here that would have been acceptable. If I had looked at Ka and I had taken Ka times 100, I would have gotten 6.3 times 10 to the negative third. Well, that is still smaller than this, so I could have approximated. So what I actually could have done was to have said that this change is much smaller than x. So this would have been approximated. Really, I probably would have done my approximation here rather than up here, because that would have been 0. And then likewise, this would have been the same thing. I could have approximated there. And you saw that when I subtracted those two, because 0.1999 is essentially 0.2. If I had done that, I would have gotten, let me erase this part right here, but I want to keep that 0.13 because I want you to be able to see how our two answers compare. Okay, whoops, there we go. So now I'm going to have 6.3 times 10 to the negative fifth times 0.2, and that'll give us 1.26 times 10 to the negative fifth, which is, you remember, that's what we had before. That's going to equal 1.0 times 10 to the negative fourth times x. If I divide both sides by 1.0 times 10 to the negative fourth, I am going to get an x that equals 0.126 molar, and then when I do sig figs, I get the same thing. So my initial concentration of benzoate is 0.13 molar. So that tells me if I want to prepare this buffer, what I need to do is I need to create a solution that is 0.2 molar in benzoic acid and 0.13 molar in sodium benzoate. Okay, second example. This is a little bit different because here I'm looking for moles of ammonium chloride. I'm adding that to 2 liters of ammonia, and I'm forming a buffer whose pH is 9. So that's my given information. We are adding a solid, we're adding ammonium chloride to this solution, and they're telling you here that the addition of it doesn't change the volume. So that means that I don't have to worry about recalculating molarity or anything like that. And then Kb is given. Okay, so what I can do here, I can set up an ice chart. So if I do that, I'm going to start with the weak base, which is ammonia, plus water. Ammonia is a base, so it's a proton acceptor. So we get ammonium and we get hydroxide. And if I set up that ice chart, I will X out water, and then I've got my fence. Now, ammonium chloride is my conjugate acid of ammonia. And ammonium and chloride are both ions, so this is my ionic compound or my salt. So here's my weak base, here's my conjugate, I have a buffer. So I want to fill in what I know. And I know both of these are included in this 2 liter, so under ammonia I can just say 0.10 molar. I don't know what ammonium is, that's my X, and initially I have no hydroxide. Now, I can do this like I did it before. So let me show you the setup for that, because I want to show you a different way to solve. I can say I've got a pH of 9. So my pOH would be 10 to the negative pOH. So that would be 10 to the negative 5th. So that concentration is 1 times 10 to the negative 5th, and that's what goes here under hydroxide. And I got that by taking 14 minus 9 to go from pH to pOH. Now, like last time, I can't assume that these two are equal to each other because at equilibrium, because I didn't start with the same amount. But I do know that hydroxide went up by 1 times 10 to the negative 5th, and so did ammonium, 1 times 10 to the negative 5th. Ammonia went down by 1 times 10 to the negative 5th because it's on the other side of the fence. So now I want to fill in my equilibrium line. I've got 0.1 minus 1 times 10 to the negative 5th, x plus 1.0 times 10 to the negative 5th, and 1.0 times 10 to the negative 5th. Now, I could go ahead and substitute this into the expression and solve. Or, if you remember when we did salts, we introduced you to Henderson-Hasselbalch. And Henderson-Hasselbalch was pH equals pKa plus the log of the conjugate base concentration divided by the concentration of your acid. So when you have that conjugate acid-base pair, you can use Henderson-Hasselbalch. Well, if you think about the relationship between pH and pOH, we could also say that pOH is equal to pKb plus the log of the conjugate acid concentration divided by the base concentration. So we are going to use this version for our problem here. So let's go ahead and substitute. What am I doing here? Okay, my pOH was 5. That is equal to pKb. Remember that pKb is equal to the negative log of Kb. So that is negative log of 1.8 times 10 to the negative 5th plus the log of the conjugate acid. If this is my base, then this is my conjugate. Whoa, my pen's flying all over. Sorry. This is my conjugate acid. Don't know what that is. I'm going to say X. I could do X. I could do X plus 1 times 10 to the negative 5th. But if I think about the size of my Kb, that times 100 is much less than 0.1. And so what that tells me is that the change is negligible in comparison to the 0.1 or the X. So what I'm going to do there is, just kind of ignore these. But I didn't have to tell you all of that because you really, with Henderson-Hasselbalch, you just use initial concentrations. Use this line. Sorry, I hope I didn't confuse you there. So now I've got Okay, so I'm taking these initial concentrations. I have my X here for the conjugate acid. I'm going to use 0.10 here for my initial base concentration. So this equation is what I'm solving. So if I do negative log of 1.8 times 10 to the negative fifth, I will get, I haven't used orange yet, 4.74. So I want to go ahead and move this over here. So if I do 5 minus 4.74, I get 0.26. That will equal the log of x over 0.10. Okay, so now when you are dividing logarithms, they are subtracted. So log of x minus log of 0.10. And if I do the log of 0.1, I get, let's do this color, -1. So I really have 0.26 equals the log of x minus a -1. So this really gives me a +1. So let's go over here. So I have 0.26 equals the log of x plus 1. I'm going to move +1 over here, so I'm subtracting 1 from 0.26, and I get -0.74 equals the log of x. Making you use your math skills here. So now, to get rid of the log, I do log to the, whoops, no, I do not do that, sorry. 10 to the -7.4 equals 10 to the log x, which really becomes x. So if I do anti-log, which is 10 to the -0.74, I get 0.18, which is a molarity. That is my x right there. So that is my initial concentration of ammonium. Now, I need to go look at what the problem actually asked me for, and it wanted moles of ammonium chloride. So I need to solve for that right now. So I have 0.18 moles per liter of ammonium. So to get just moles, I need to multiply by liters. And I have a 2-liter solution. So 0.18 times 2.0 is 0.36 moles of ammonium. Now, if I actually wanted to prepare this buffer, I would, I'm going to erase some of all of this very nice math. Okay, so like let's say I had a beaker, and this would be 2 liters of 0.10 molar ammonia. So that's what I have here. To that, I'm going to add some ammonium chloride. And I can't measure 0.36 moles of ammonium. So what I would need to do, if I wanted to actually make this buffer to be able to use in lab or for whatever reason, I would take my 0.36 moles of ammonium. Now that's a 1-to-1 ratio with my chloride ion, so I really have that many moles of ammonium chloride. You know, if I had 2 moles of one of the ions, I would have to do stoichiometry to figure that out, but I don't. So now I want to go from moles to grams. I know the problem didn't ask you that, but I think it's good to look at this. So the molar mass of ammonium chloride is 14 for ammonia, plus 4.04 for hydrogen, plus 35.5 for chlorine, and I get 53.54. So I'm taking those two numbers times each other, and I would get, sig figs, I really need 2. I ended up with 19.27 grams of ammonium chloride that I would need to add. But if I were doing sig figs, I would say 2 sig figs. So I'd need 19 grams of ammonium chloride added to this solution to actually prepare this buffer that's buffered at a pH of 9.